All right, welcome to my presentation on the linear time union find, which is a special case of the disjoint forest algorithm. So the basic idea behind this is that we assume some sort of clairvoyant knowledge of what the unions coming in to this data structure will look like. So this is just like a traditional disjoint forest problem where you have a set of n elements that you wish to perform union and finds on, and then you have m interspersed union and find operations. And so what you can do is with these union operations, as I've shown here, is that you can actually construct sort of a tree out of these. And we call this tree the static union tree. And so the tree has a couple of properties. The main one being that any subtree um, is any subtree or the root node of the subtree is a valid set with the root node being the set name at some point in time during these union operations. And then it also has this other property where the ordering of the children for any parent node doesn't really matter. It's sort of like how you can flip around, you can change some orderings of the union operations and still have the same end result pretty much. And so we're going to be comparing this linear time algorithm to the traditional disjoint forest algorithm. Here we refer to as an alpha algorithm to sort of show that it has this inverse Ackermann component. And so our linear algorithm will be linear of O big M plus N, and then we'll also incur this big O of N pre-processing step. And so you might be a little bit skeptical. You should be. This is more of a theoretical exercise than anything actually useful because this pre-processing step is a little involved. Okay, so to get into it, the first thing we're going to introduce is this idea of microsets, which are these partitions of the elements within this tree. And so I'll get into how we actually construct these microsets, but I want to establish these properties to show that when we construct it, we satisfy these properties. And so the first property is that each microset we construct will have strictly fewer than B elements. And B is this parameter that we'll tune later. And we'll set constraints on how to actually choose B. And so then the second property is that every single microset will have what we will refer to as the microset root. And the microset root is essentially the first common ancestor of every single node within the microset. So you can see in this example, I have the microsets outlined in green, and then the microset roots are, each microset has a root, which is the red arrow, basically points to which the root of each microset. And then our final property is the number of microsets we have is bounded by big O of N over B. So the number of elements we have in total divided by the maximum size of each microset. Okay, so now on to the construction of our microsets. So we have this algorithm that basically relies on two ideas. One is that we go through the tree in this post order. And then the second is that we assign this integer value we call d of v to be the number of seen nodes, the number of seen children to any parent node v that is not yet in a microset. Okay, and so we'll walk through this algorithm and it will become apparent why this is useful. So I've already done this algorithm on the first set of leaf nodes in post order because it's trivial. You never really get past step one. And so starting here at the first interesting node, which is this B node indicated. So in this case, V is B, and then we start at the first child, we'll call it W. And in this case, that first child is G. And so we'll assign this, an important thing to note is that the counter always starts at 1 because we include the parent node itself when we're talking about the number of nodes that are not yet in a microset. The parent node will always not be in a microset when we're creating these microsets. And so we set this counter initially to 1, look at the first child in the microset, and then we'll set up this kind of special threshold of B plus 1 over 2. So basically, if we see enough children such that all of the descendants that we would have seen sums up to greater than B plus 1 over 2, then we'll break out of this loop. But until then, we'll just keep iterating over children, or until we've run out of children to iterate over. And then every time we're going to add up the child's weight to our weight, because the child will sort of encode how many of its descendants also are not yet in a microset. And so we iterate through this a couple of times, and then on this iteration, we see that we've sort of surpassed this threshold. So we go into step 3, where we create a new microset with all the elements that we've seen up until, but not including the child node that we have not processed yet. And then when we do that, we'll set the the root of this microset to be the parent node that we're currently at, and then we'll reset the counter back to 1 because all the nodes that we've seen and processed so far are now put into a microset. So we remove them from this counter. So you can see here, then we process the next node, we update our counter on the parent node, and then we're out of children to process, so we've got to move on to the next node in post order, which in this case is this leaf node on the right-hand side of the tree. And so from here, I'll just skip through the algorithm. I'm showing only where we create microsets, so mess that up. But the next microset we create is with E and F, and then we create B and I, C and D, and then finally we get all the way back up to the top of the tree. And after we finish processing all the children of the root node, any children that are not yet in a microset created in the step 3 process, we put in a new microset and set the root of that microset to be null. So this is sort of like a special kind of edge case microset. And so with this construction, we'll now prove that these properties that we've stated hold. So the first property is that each microset has fewer than B elements. We can see that any child of the current node we know has to have a weight less than B plus 1 over 2, or else we would have created microsets and then reset that counter. And so the count on the current node plus the child node has to then be less than B plus 1 over 2 because this threshold has to be set on both nodes. And so then when we create the microset, we're not actually adding the parent node to the microset. So we can actually take this sum and subtract 1, and that is the number of nodes then we're adding to the microset. And so then we can see that when we take that sum and subtract 1, it is strictly less than B. So this first property will hold. And the second property always holds clearly by construction, except for the last microset, which, like I said, is an edge case. So we just kind of ignore it. Then this third property comes about because we can kind of guarantee strictly that each microset will have strictly greater than B minus 1 over 2 elements because of that threshold that we set. So then if we take the total number of elements and divide it by this threshold, we get an upper bound on the number of microsets. And then we add a plus 1 onto the end to count for that last microset. That's sort of, the odd one out. And this is clearly big O of N over B. So our properties hold, which is fantastic. All right, and then just last little bit of info on this microset creation. When we create these microsets, we're going to assign them integer labels in sequential order, in the order that they're created, starting from 0. And so then we're also going to construct this lookup table called micro V, where if you give it an element named V, it will return the index of the microset V is located in. And then we're also going to, as we construct these microsets, every element in a microset will get an integer label, sequential integer label starting from 1. So you create a microset with 3 elements, they'll have labels 1, 2, and 3. And this is local to each microset, so you reset the counter every single time creating a microset. And so then we'll construct a second lookup table called number of V, which basically, if you give it an element V, it returns the index of that element with respect to the microset it's in. And so then you have these 2 indices from a single element, so then you can kind of do the reverse operation by constructing this third lookup table, which is basically give these 2 indices and it will return the element uniquely associated by these 2 indices. So that's everything about constructing the microsets. So now we're going to go start defining some functions. The first function we want is called microfind. And what microfind is going to do is it's going to return, if we give it an element V, it is going to return the nearest ancestor to V that is within the same microset as V, that is a set name at the current time in operations. And then if no such node exists, then we're going to return the root of the microset. And then we're going to construct this function to have an O of 1 runtime. And so just for some examples, you can see I have the set names marked in red, and then some examples of what microfind would return. So the first case is the microfind on G. There is no set name within this microset that is parent, that is an ancestor of G. So we just return the microset root. The second case, I is in the same microset as B, and B is a set name, and B is also an ancestor of I, so we return B. And in the third case, we consider a node to be its own ancestor. So then to start to construct microfind, we're going to create multiple lookup tables. It's pretty much the only way we're going to get this to work in O1, right? To keep track of which nodes are set names, we're going to create what we call mark tables. And we're going to create one mark table for each microset. And the way this is going to work is that if a node is a set name, then it will have a value of 0. And if a node is not a set name, it will have a value of 1. And so kind of clearly is that each microset has up to b-1 elements. So therefore we can represent each mark table as, a bit string of b-1 bits. So therefore it can be an integer within this space shown here. And so when we initialize these mark tables, we'll initialize them all to 0 because every single node will be its own set. Okay, and so then the next table we'll create is called the parent table, which holds these inner microset relationships, where if you give the parent table if you look at the parent table for some element with an index j, it will return the parent to that node that is within the same microset index k, and then if it doesn't have a parent within the microset, it will return 0. And so we'll note that each one of these k's can be represented with ceiling of log b bits, because you can only have integers from 1 to b in a microset of b elements. And then, so then each parent table can be represented as you have b-1 partitions of log b bits. So you have an integer with b-1 log b bits. And so we'll assign this integer to be called a q, and it's within this range shown here. However, we will note that not every single q in this range is a valid parent table. So you can kind of imagine the parent represents sort of a snapshot, like a cutout of a graph structure. And so the first idea is that each partition should never point outside of this table that we're in. So each partition needs to look at somewhere else within this parent table, the parent integer that we've defined. So there's b-1 partition, so we should jump to a valid partition. And so then each q also has to represent an acyclic digraph, basically a snapshot of part of this tree. And so I've shown here basically what each parent table looks like if you were to kind of break it up into the integer parts of the partition. And so you can kind of see how it creates sort of a directed graph where we start in the case where we don't have any parents, everything is 0. But if we do have a parent, then the value at that position for the index will be the parent. So we can kind of look and see, all right, we can kind of follow each partition around until we hit a 0, right? And then if we never hit a 0, such as in this case, then it creates a cyclic graph, and that's an invalid parent table. Okay, so now we can finally move on to constructing this answer table. So we're going to take in a parent table, integer, a mark table as an integer, and then some sort of element index as j. And so we're going to construct this answer function to be basically do all the work of the microfine operation. So it's going to return an index k if k is the first marked, it's the first set name ancestor of this given j node within the same microset as this j node. And so we can kind of define this mathematically as sort of reapplying k, or reapplying this parent table multiple times, sort of looking around in the parent table until we hit some index k, such that when we look at the mark table, the k has a set name of 0. And then basically at each step before we found that k value, the mark table always had a value of 1. And if we can't find a k like that, then the answer is 0. And so then we construct the answer table to do all this in O1 runtime by making it basically a 3D array, a giant lookup table. And so you can see the dimensions of this array, or sort of the bounds of each one of these integers going into the array. So we initialize this basically to all zeros, and then what we'll do is we'll just iterate through every single value of q, s, j, and basically pre-compute these answers. And so then to make sure that this pre-processing step happens in O of n time, we basically take the total dimensionality of this table, which is parameterized by this b value, and basically say b has to be chosen such that the giant size of the table is O of n. So then we can implement the microfind, basically just doing each one of these lookup tables. And then once we get the k value out of the final answer table, we just basically return this index back into our element space using this node function that we defined earlier. And then if we can't, then we would just return the root of the microset that we're currently in. And so then the final thing we need before constructing our union and find operations is to have this macroset data structure on the microset root nodes, which is basically going to be controlled by an alpha algorithm, so a union find alpha algorithm. And we're going to have the macro find and macro union are going to be our find and union respectively. And so these are only going to operate on the microset root nodes. And this is basically going to be used to merge microsets together for more efficient computation. Now that we have all that, we define our union and find. So we'll define the union first. It's relatively simple, since we can only do a union between a child and a parent, by the construction of the static union tree. all we need to do to update a child node is basically set its mark table value to 1. So you can see that here, relatively trivial O(1) runtime. So the next thing we're going to do is define the find function using pretty much everything we've seen before. It's a little bit complicated at first glance, but we'll walk through it and prove that it is correct in that it will find the set name of the given element V. So basically, if we reach step 3, that means there is no set name within the current microset. So we need to start looking at microsets higher in the tree. And so we establish this X value once we hit step 3 to always be a microset root. So that way we can use these macroset operations to sort of jump around to different microsets and then look inside of each microset. As we're going up the microsets, as we're looking up the tree, what we can do is basically say, like, if we've already started at some path and we're looking up the path, right? Then there's no sense in rechecking every single microset along the path that we've already checked. So as we're moving up the microsets, each time we move up the microset, we can basically say, all right, well, we've already checked all the microsets below it. So it's sort of intuitively similar to path compression, where we just kind of create this link between the bottom microsets in the path to the topmost, the last known good microset. Putting this together with a definition of microfind, basically, if you keep calling microfind, microfind is defined to only such that the only set name between the given node and the node returned by microfind can be the node returned by microfind. So if you keep applying microfind, eventually you'll find some ancestor to the original node that is a set name. And so if you put all this together, you can kind of see that the algorithm will always return a set name, the first set name to the given node. And so if we next move on to the runtime analysis, we note that this algorithm is dominated by these macro find operations. And so we can kind of turn this into like a regular alpha algorithm runtime, where basically the number of elements is the number of microsets, which is big O of n over B. And then the number of interspersed macro find and macro union calls is M, because in the worst case scenario, you can hit macro find M times. And then you can only do a big O of n over B macro union operations, 1 for each. You can only macro find the total number of elements inside of the, you can only macro find the total number of microset roots. And so you get this kind of expression, gross looking expression for the runtime, but you can see it just kind of basically boils down to a basic alpha algorithm runtime. And so then the question is, how do we get from this runtime to a linear runtime? It's going to be 2 things. First off is we're going to put 2 lower bounds on B. So the first lower bound comes from the microset construction. It has to be, B has to be greater than or equal to for microsets to even work, right? And then if we say B is greater than or equal to 2, then big O of n over B has to be big O of n. And then the second thing we're going to do is eliminate the inverse Ackermann part of this by basically showing it is a constant runtime by setting a lower bound of big omega log n on B. And then to facilitate this proof, we just pull from the earlier work, which actually proved this inverse Ackermann runtime. So we take this definition for the inverse Ackermann function, and then we also take this special piece of the Ackermann function where if the first parameter is 1, then it can be expressed as basically 2 to the power of the second parameter. And so basically what we'll show is that in this inverse Ackermann function, if z is always equal to 1, independent of m or n, then this inverse Ackermann function part becomes O of 1. And so basically we take these x and y values shown on the previous slide, substitute in our own values. And so I've done that here. And so we expand out the logs part, the less than or equal to part. Basically when we substitute in n and then log n for B, we get log of n minus log n is less than or equal to the Ackermann function part. And so then we substitute in this idealized z equals 1 Ackermann function, and then we substitute in our exponent and expand out. We can see that we actually get 2 times log raised to the m over n power of n. And this was for a sufficiently large value of n. This is greater than or equal to the left-hand side. And will always hold because m is defined to be greater than or equal to n. So this exponent is always at least 1. And so then the inverse Ackermann part is O of 1, and then we take the other part over big O of n over b is O of n because b is greater than or equal to 2, and we can show that the whole runtime of the find function is O of n plus n. So it's linear, which is fantastic. And so just to wrap up everything we've shown, if we have a static union tree of n elements and m interspersed union and find operations, we can process those operations as big O of n plus n time, plus an O of n pre-processing step, which is the microset and table creation. And then we have this tunable parameter b. We created these constraints on b. So the first constraint is b must be greater than or equal to 2 for the microset creation. B must be big omega of log n to facilitate our runtime proof. B, the answer table size has to be big O of n in order to make the pre-processing step big O of n. And then the final one that we haven't shown before is basically the parent table. The number of bits in any given parent table has to be less than or equal to the number of bits in the integer word size on your machine, basically to enable these lookup times and constant lookup times. All right, and that is it. Here are my references. So the first reference is basically what this algorithm is, the paper this algorithm is based off of. And then the second reference is basically some information pulled to facilitate the runtime proof of the find function. So yeah, thank you for your time.